Good morning. Can everybody hear me? My name is Radha Cherkova. It's a great pleasure to welcome you to SIGMOD 2017 in Chicago. So just a bit of registration stats. Currently, as of yesterday afternoon, we have 771 registrations. And so this is the breakdown. Conference only, conference and workshop only. The conference program is to be overviewed by the PC chair, Dan Suchu, shortly. Let me take this opportunity to thank our sponsors for their generous support and contributions to this wonderful conference. So a few announcements. So we are putting all the up-to-date information onto the conference website. So this hotel is a bit tricky as far as the layout goes. The schedule page has the layout of the hotel and meeting rooms. There are also screens in the hallways that show the structure of the meeting rooms. For the location of your poster and demo, please check the posters and demos floor plans. This is under SIGMOD program. There is a pointer to posters and demos. So a couple of announcements for today and tomorrow. Today, the awards will be announced at lunch. And tomorrow evening, we have a wonderful special event at the Shed Aquarium, the banquet. It is a really short walk from here. The conference website has all the information about the time and the transportation options. And with this, let me give the podium to Jun.
Thank you, Radha. This is Jun Yan from Duke University. So I just have a few things to add, details, but important ones. So if you plan to do session hopping today, let me just tell you that a couple of Sigma sessions are going to be in the lake rooms, which are located on the 8th floor, number 8. Okay, so we had some volunteer time the walk from here to the 8th floor. It's going to take you between 3 and 5 minutes. Okay, so keep this in mind. All right, just make it to the lobby elevators. Go to the 8th floor, follow our signs. Okay. Every elevator actually goes to the 8th floor. Thank you for the clarification. Okay. Another announcement, so pod session 1, tutorial session 1, we have basically an update which is different from the booklet. So it's going to be random sampling on big data by Ke Yi from Hong Kong University of Science and Technology. I think these are all the other things I want to add. As you all know, this conference, our conference, has come a long way, both figuratively and literally, from North Carolina to Illinois. And this would not have been possible with just the absolute outpouring of support from this community and the unity that we show. So we're really appreciative of that. And this would not have been possible without the hard work of all the volunteers. So if you see them, thank them. They wear purple T-shirts. We are here to, ready to help you in any way can. And also, did I mention that we're actually live on air? Okay, so live from Chicago. This is SIGMOD 2017. And here's your host, Professor Dan Suchu from University of Washington.
Thanks, Dan. Okay. Yes, hello everyone. I'm Dan Suchu. I'm the program committee chair. So this year, we have actually a slide for this. This year we have 100 amazing papers, 96 research and 4 industrial. We have 2 keynote sessions on grand challenges in data management. And we have 30 demos. This is a very exciting program, and the only thing between you and this exciting program is me sitting here. It just takes me a few minutes to describe to you what the program is about. So this year, you will see every paper 3 times during the same day. A 1-minute teaser talk, then a full presentation, and then again during the poster session in the afternoon. The teaser talks are new for this community. Others have been doing this for many years. Every presenter gets 1 minute to sit here in front of the entire community and present their work. We as a community have the chance to see all the papers that are presented at this conference to see what goes on, what happens in this, at this conference. After the teaser talks midday, we move to the actual sessions. Every paper has a comfortable 25 minutes for presentation and questions. And then again, in the afternoon, the same papers will have 2 hours of a poster session where you can really discuss with the authors and go deeper into the technical details. Everything is color-coded. The sessions are color-coded. The rooms have the same colors, and the areas in the posters have the same colors as the sessions where those papers were presented. So please check the colors and the icons or the little signs for the session that you are interested in. Also, the papers are aligned at time-wise, so if you want to jump from one session to the other, you can do this. You can get from sessions on this floor to those on the 8th floor in 3 minutes. June tested this, which is exactly the question and answer time, so you can actually switch between sessions. A final note about the research papers. This year we are doing live streaming, and I'm going to ask the authors to please be 50 minutes before their session in the room and set up what is needed for live streaming. And I hope everybody here will actually attend the sessions live, but if you have friends out there, tell them that live streaming works really, really well. I tested it yesterday on a pod session, and it's actually it works very well. The organizers have done an amazing job. Okay, about the keynote. So in our conference, we cover a lot of topics, and many of these topics are actually at the intersection with other areas in computer science. This year, for the keynote sessions, we have chosen some topics that are core to our community, that define us and unify us. We are going to discuss transactions and approximate query processing, AQP. These topics are of fundamental importance way beyond databases. They are important in many areas in computer science. However, we own these topics. The key innovations in these topics, they came from this room, from people sitting right here in this room. And I'm confident that the future breakthroughs will come from young researchers sitting here on one of these chairs. So we invited 5 distinguished speakers who are very active working on these topics to tell us about the current research that goes on in these areas to keep us up to date with the latest innovations in this field. I really, really look forward to these sessions. And without any other interruption, I'm going to hand it over to Magda Balazinska, who is going to share the first session on transactions.
Good morning, everyone. So as Dan was mentioning, transaction processing is a really exciting and important area in our community. It has always been our bread and butter. And today, it continues to be really important and exciting because we have many changes in the landscape of transaction processing. We have access to new hardware that changes the equation. There are new applications that need transaction processing, but the requirements are different. We need to optimize for novel metrics. We now have access to large servers with very large main memories. So many changes, a lot of excitement, and we have 2 great speakers today that will tell us about the challenges and the opportunities around all of these changes. Our first speaker is Professor Anastasia Ailamaki from EPFL. So we all know Anastasia. She has a very long track record of innovations in the area of database systems on new hardware. In fact, she's the founder of the Daemon workshop that I know many of you attended yesterday. She also has a very long list of awards. I could only fit a few on my piece of paper. They include, Sloan Fellowship, Endowed Chair, European Young Investigator Award, many Best Paper Awards, an ACM Fellowship, and many more. So we're very excited today to hear from Anastasia and hear her vision on the next 700 database management systems for transaction processing. Thank you.
So, is this one? Okay, got it. Thank you, Magda. Thank you, everyone, and for being here today, and Dan for this honor. Oh, yeah, well, it's more useful, bigger. Yeah, I'm really excited to talk about transactions because, as Dan put it when we discussed the subject of this keynote, transactions are hot and cool. And they are indeed. So today, I'd like to talk about a few things that have been happening, are happening, and will be happening, in my view, of transactions from, of course, the system side. This is work that has been done with my wonderful systems group at EPFL, the Data Intensive Applications and Systems Lab, and in particular, the two people who have helped mostly with putting together and researching this talk was Raja Puswami and Utku Sirin. So, enterprise data management was a simple situation in the 80s, right? We all remember the database engines that would run pretty much everything on single-threaded uniprocessors with high-performance disk arrays, and the problem was always disk I/O. But ever since then, the hardware and the applications did direct the engine design. And right after, in the next decade, the big bifurcation happened. People realized that one size does not fit all, obviously, so we had to do different things in the engine for OLTP, which handled small transactions on gigabyte scale data, well, today's numbers, back then a lot less. But the transactions were mostly real-time, handling business operations day-to-day, and OLAP, which was essentially the supporting for decision-making using the results of these transactions. The key issue was that OLAP needs the results of the transactions to work properly, so we had the extract, transform, load programs which allowed us to move the results of the transactions to the OLAP side. And that way, we could use, queries could use the transactions outputs. And that's basically a workflow that we had there. Moving on to the next decade, the big ticket item was that Dennard scaling came to a halt, and processor vendors were absolutely unable anymore to raise clock frequencies without substantially increasing power consumption to the point that the chip couldn't operate. And this led to the birth of multi-core processors. And the big ticket item there was that we had explicit thread-level parallelism. So essentially, the ball was back on the software to take advantage of that. So the big challenges research-wise for OLTP engines were to transition from multitasking-style parallelism to true concurrency coming from the hardware resources. So we focused on developing scalable synchronization techniques for exploiting parallelism powered by multiple processors, and OLAP research on the other side did inter-query parallelism and intra-query parallelism technique to exploit again the parallelism. But then toward late 2000s, and then of course, but then of course this went on for many years, these research topics. But still, if you run numbers on transaction systems, even running very, very small transactions recently, most of us see lines like the one that you see here, which basically means that initially as the number of cores, the number of sockets goes up, transaction throughput goes up in a nice curve, and then afterwards things fall down and then plateau. Okay, and that means that the bottlenecks are there and continue to be there, and transaction contention is not a solved problem. And finally, in the more recent years, DRAM price fell so much that it reached a level where we could fit one server with several terabytes of memory. And at the same time, we could fit a database, a whole database, or even the working set of an OLTP workload in the same memory. So in-memory OLTP took over, and this is a flurry of research, even today, on scalable main memory engines that adopt very different designs of data structures and algorithms when compared to the disk-based counterparts. So the bottom line here is two things. First of all, applications and hardware dictate OLTP design and research. Second of all, highest throughput OLTP engine is a big deal, because the higher the throughput of the OLTP engine, the faster the data can get to the ETL filter and go out to the warehouse for OLAP use. Okay. However, there's several game changers today that I want to talk about and see how they will affect OLTP engine designs in the very near future. First one, you've all heard of it, it's power. This is one of the many numbers you can find online in reports from Gartner and other corporations. And our very own James Hamilton has done extensive work there. Data centers cost a lot to power. And most of this power goes to powering servers. Okay, and you may say that these are mostly analytics. Well, Amazon's Redshift in the middle of 2016 was reported as the fastest growing database on the cloud. Then a few months later, just 3 or 4 months later, Amazon itself announced that Aurora, its own OLTP engine, is now the fastest growing engine on the cloud. Because this has very much to do with OLTP, and we should work on power issues when running OLTP engines as well. But also applications are changing at the same time. So real-time operational analytics, or analytics 3.0, is a new big ticket item, which essentially means that we need to eliminate the 3-stage workflow, OLTP, ETL, OLAP, and actually run everything on one engine, OLTP and OLAP on one engine that accesses one database. And that, although it takes us a bit back to the 80s in our thinking, it becomes a pretty daunting process in light of the hardware development. And that's my last bullet there. So we see in the hardware what I call a specialized generalization. At the processor level, we have architectures that get more and more diverse. For example, ARM's Big Little, Xeon 5, and the omnipresent general purpose GPUs. Then we have interconnects, and these technologies are basically rising up to overcome the PCIe bandwidth issues. So QPI, ARM shareability domains, and the single chip, the cloud on the chip from Intel are using interconnects that are faster now, and also NVIDIA is coming up with NVLink. But also, more importantly, those interconnects implement, those architectures implement coherence protocols that no longer give you coherence across the whole board. So you can either configure it, or actually you have to do it on the software side, especially when talking about Intel's SCC. And finally, at the memory level, we have non-volatile memory, which is taken over, and the 3D memory, the 3D X-point memory, which these things you may tell me, why do we care about this stuff? Where it's very well known that data placement in memory is extremely important for performance. And so the database has to work hand in hand with that level. So there's a lot of challenges and opportunities to discuss and take advantage of here. So I'm going to talk about two things. The first one is going to be OLTP engine design for high performance, but at the same time, low power. And I'm going to get back to the topic that's very dear to a lot of us, utilization of core resources. So this is a pretty simple experiment where we run a one-line transaction, one customer, read bank balance, absolutely no contention. The ideal line is a linear scale-up as we increase the number of worker threads, right? And even there, when we have no contention, you see that the normalized speedup is much less when you actually run the system on a multi-core server. And it can be much less by a factor of 1 to a factor in this experiment of 2.5. And I underline that that's a lot because it's a very simple transaction. It's completely unrealistic. It shouldn't have any problems, right? And if you look at how busy the processor really is, this processor could be giving you the results of 4 instructions every cycle, because that's how it's made. But on average, it gives you only the results of 1 instruction per cycle. So the net is that we can't exploit the abundant parallelism, and we underutilize the cores. So the question is, what's going on? So these are the familiar CPI breakdowns, right? The execution cycles in blue. When I run, when running on-disk transactional workload, SureMT is a prototype, and then a database, a commercial database. And we can see that less than 40% is actually utilized. So the processor is waiting for memory most of the time, again. But then in-memory transaction processing engines are gaining ground because of how large the memories are today. So the question is, do they do better? I mean, there's no disk component, they have to do fewer things, so maybe they do better. The answer is, well, they could, but they don't. Okay, so speed-wise, they're probably faster. But in terms of utilizing the hardware, it's actually the same situation, okay? And so looking a bit deeper in there, we see that if we break down all of this time, all of these stalls, this is just the red part now, right? Broken down into 3 levels of cache. We have first level, second level, and what we call last level cache, which is really the 3rd level in today's processors. And then the I or the D means stalls because of instruction search and stalls because of data searches. And then we can see that all of the systems, and I'm running actually here, we're running TPCC with 1 worker thread. So it's, again, a relatively simple and short transaction workload. And we see that across the board, we get first level instruction cache misses, that give us a lot of stalls, which means that the processor is still unable to get as many instructions as it needs in order to execute with high performance. And then the standing out case, of course, is Hyper, which is a state-of-the-art transaction processing system developed in Germany by Thomas Neumann and Alfons Kemper. And there are significant optimizations done for just-in-time compilation very close to the machine, right before the transaction gets executed. And though this results in essentially much fewer transactions, having to execute much fewer transactions. The problem, however, that rears up its ugly head is that when you do that, you inevitably increase data misses because you no longer have affinity to what's going on with the data. The net-net is that this system is significantly faster by a factor of a couple of orders of magnitude. But its utilization of the processor, which is my point here, is just as bad because you have to pay attention to all of the stalls, and because the compilation happens irrespective of data. We've run other systems out there. Silo, very notably, from Sam Madden at MIT, performs really well and actually is better than Hyper, although it doesn't use just-in-time compilation. It's better than Hyper in utilization of the resources. But my point here is that the stalls for instructions are always there, okay? And especially in the case of this workload, the longer the transactions become, the more the instruction stalls will become because they won't fit in the cache. So we need to take advantage of some opportunity there in order to fix the first level instruction cache without ruining the data cache behavior, okay? And I'm going to refer to one example of work done in our group by Pinar Tozun, who's now at IBM, and the University of Toronto as collaborators. And there, Pinar put together a rudimentary picture of what is it that we really do when we run transactions, especially TPCC as an example here. And there's a few operations that we repeat with different and in different orders. This is a simple example of some of the operations that we do, and say that our workload has a transactions that starts with with an index probe, then updates a record, and then takes a branch to complete. Okay, and this transaction, depending on the input, instantiates as transaction 1, where the branch is taken, or transaction 2, where the branch is not taken. So Here, you can immediately see that there is, across these transactions, everything that you see having the same color is the same code. Remember, we're talking about instruction misses, okay? So this is the same code. So there's a lot of common code, and Pinar's research analysis showed also that there is very low data overlap across different transactions when running together. So transactions are not doing the same things, but operating on different data. And that's a big opportunity to take advantage of. Immediately, one could think that transactions might communicate with each other to coexist and take advantage of the same code so that they don't have to reload it in the caches. Well, that's actually very difficult to do in practice because it carries a lot of overhead. So what Pinar did instead is that she said, I'm going to make she observed how transactions, first of all, are assigned in a conventional core system. So these are two transactions color-coded depending on what they are executing. And transaction 1 comes along, and it will fill the first core's cache with the red instructions, and then it will continue in the first core, throwing the red instructions away and putting in the yellow instructions. And T2 comes along and fills the second core's cache, is assigned to the core 2 and fills the second core's cache with the red instructions, and so on and so forth. So these transactions are running, and essentially by the time they're done, they have done 7 cache fills. Okay, these are all misses. These are compulsory misses because they couldn't have served any other way. So Pinar came up with this idea, said, why don't we make transactions chase locality? So the moment the transaction has filled the cache, there is a hardware mechanism that's triggered, which basically detects that the cache has started taking capacity misses. So the mechanism makes the transaction look other caches in the system, which might contain, based on the sample, might contain interesting instructions in them. And then the moment T1 finishes with this red block, it migrates to another core and loads that core's cache with the yellow instructions. And at the same time, T2 comes along and detects that the first core contains a good sample of what transactions it's supposed to start using, so it continues, it starts there. And then T1 finishes with the yellow part, and then before executing the green part, it migrates to yet another core, whereas T2 detects that the yellow part is already loaded in the second core, and so on and so forth. So essentially, transactions from executing vertically start executing diagonally. SLIC, the self-assembly of LU&I caches, is a hardware-only programming transparent technique. That means the programming doesn't really have to do anything to make that work. Pinar went along with more research and figured out that there is an even better thing to do to actually break the pieces before, make transactions migrate at finer grain operation boundaries and use a little bit of the program's logic to aid the migration, happen earlier even than when the SLIC does. And she got even better results with this new technique called addict. The only downside is, of course, the programmer needs to know about it because he or she needs to put in the marks of when the transaction can migrate. So back into our very simple example, there's tons of numbers in the papers, but with SLIC and addict, one can really approximate in the very simple example case here, the ideal scale-up, and effectively double the instructions per cycle we can get. But we're still not there. We still need to work toward better hardware-software integration. So I promised performance and power, and the power part is coming now. Why do I connect these two? Well, because really the core resources need to be used also for power, right? Stavros Charizopoulos in CIDR a few years back had this very interesting paper where he essentially showed that so all the time that a CPU is powered, when the CPUs are active, they dominate power consumption, and they still account for like 40% of the power consumption even when they're idle. Okay, so there's money spent powering idle CPUs here. And if we don't use the CPUs, we're essentially increasing the amount of money that's spent on powering those CPUs. So I want to advocate that we should start looking very seriously toward low power processors. ARM is a company, one of the companies that makes them. And very recently, they've come up with the Cortex series, which is a low power processor, but it's not a wimpy one. So it's got a much better performance. Okay, and you get new companies now like Microsoft and Bull, but also the Barcelona supercomputing servers basing their new machines on ARM processors, announcing that they base the new machines on ARM processors. So the question is, can we get OLTP energy efficiency using ARM CPUs? I'm just going to give you this as a teaser here. The answer is yes, and we should really seriously pay attention to low power processors. So on the side, I can't see the mouse, okay. All right, you can see the mouse. On the side, on the left-hand side at the top here, you have normalized throughput of TPCC running on the MIT prototype silo, which has been the most performance, the most efficient on low power among the systems that we researched. And there, Utku Sirin, my student, ran against ShoreMT, which is our classic prototype, well, against ShoreMT and other systems. But here you see Silo running on Xeon, which is a classical high-power, high-performance Intel processor, and the ARM Cortex A57. And the ARM is always in blue, and the Xeon is always in red. And you can see that, of course, the throughput is much higher with the Xeon than it is with the ARM. But at the same time, the power, Xeon starts from very high, from 15 times higher than the ARM, and it goes on, whereas the ARM is a lot modest. It starts from 0, and it does increase, but not as steeply. Two important points to remember here: energy efficiency and energy proportionality. Energy efficiency is essentially the result of the division between performance and power spent. So you can see here that if we divide the performance that we get for the power that we spend, we get the Xeon being really, really low, especially when you have a low number of threads, and the ARM being very high, being very, very energy efficient. Another interesting notion is that of energy proportionality. This means that a system should consume, if it's running, say, with 8 cores, it should consume half of the energy than if it's running with 16 cores. So it should automatically tune its energy consumption with the cores, with the number of cores, the number of resources that it actually uses. And there, you see that as we increase the number of threads, the ARM is relatively stable, so it achieves energy proportionality, whereas the Xeon, especially when you use fewer threads than those available, actually has really bad energy proportionality, which means that it consumes much more power than it should. And that's because it starts from really high. So this is a promising situation. We should look at low power processors. We should see how we can use them to help low power OLTP engines. But we shouldn't forget that these days we're running on memory, and running in memory OLTP means running on systems with a lot of memory. Okay, so this is an interesting graph which shows you that memory is not cheap on power. When so this is a system that can take from 8 gigabytes all the way to 6 terabytes of memory. And this is the power, this is how much power it spends. Its CPU will be the same across, no matter how much memory you have in the system, it will spend the same amount of power. And you can see here two things. First of all, from 16 to 128 gigabytes of memory, you have 3 times the power when you multiply the capacity by 16, from 8 to 128. And then when you multiply the capacity by another 4, you pay another factor of 10 in power. And then, third thing is that the increase is not linear anymore after a point. It's actually exponential. And you get to the point where if you load your processor with anything more, your system with anything more than 3 terabytes, you will get a whopping from anywhere from 1 to 2.5x more power spent by the memory than by the CPU. And we need that memory in order to store our big OLTP databases. So DRAM is making a comeback and closing the gap between power consumption, so we should really be looking at that as well. In the last few minutes of my talk, I'd like to speak to you about a heterogeneous age gap, which is the new effort coming out of the industry and from the research community to run high throughput OLTP and low latency OLAP on fresh data. As you saw before, and as we all know, this bifurcation between OLTP and OLAP in the business world meant that we have to wait until we're able to use the latest transactions results for the ETL system to work and transfer them over to the warehouse. So people want now high throughput OLTP and low latency OLAP running on the same engine and on the same database. And that has the fancier name HTAP. Okay? So HTAP has a few requirements. First of all, it requires massive parallelism. Well, that's okay. We have massive parallelism. Okay? That's what hardware has been given us since the dawn of time. The problem is that the parallelism today is heterogeneous. Think Big Little, Intel's HARP, and so on, Xeon Phi, and so on and so forth. All the new processors today give us a variety of cores to work with. And we can't exploit that. HTAP engines today cannot exploit that. The second requirement is that for OLTP and OLAP to work on the same data, of course, we need system-wide cache coherence. Okay? But that's not necessarily true. There is shareability domains by ARM, which is essentially a way to group together processors that are going to be coherent and parts of the system that are going to be coherent. But most systems today start relaxing the cache coherence. And of course, Intel's SCC doesn't give you coherence at all. It's a completely shared nothing. You have to implement coherence at the software level. We're not really sure how to work with that yet. But of course, we can say we can do a message passing system. We can implement HTAP as a distributed system and work on message passing. But then you have global shared memory. And even better, today's GPUs actually see that shared memory. And it's shared across accelerators or co-processors and CPUs. So that's a non-tapped resource. We can't exploit it if we actually go to distributed systems. So there is a ton of great research to be done here. We had a paper earlier this year at CIDR where we looked at some of these issues, but the two trends at the high level that we need to be thinking of is, first of all, that CPUs are specialized. So in terms of coherence, we used to have one coherence domain, and now we have many coherence domains in today's processors. So CPUs become from general purpose to customizable feature specialized processors. GPUs at the same time, that used to be those processors that nobody really paid attention to because they can only do one thing well and they were held to program. Today, they have both better programmability with unified memory, dynamic parallelism, and so on and so forth, but also they have fantastic interfaces. NVLink is the one that's being pushed hardest by NVIDIA, but others, which basically overcome all the PCIe problems. So GPUs from niche accelerators are becoming general purpose processors because we can program them and use them, and they can see the same memory as CPUs. Well, so for HTAP, today we're moving to this era of heterogeneous HTAP. The ideas in here belong to Raja Puzwami, Manos Karpathiatakis, and Dani Chaporovich. And this essentially says that we will be running OLTP and OLAP on fresh data, but the engine will be running on across the board on all of the available hardware. In this case, I have a machine which has a part of it with task parallel cores and a part of it with data parallel cores. So heterogeneous HTAP needs to store data in shared memory so that everybody can access them, needs to run OLTP workloads on the task parallel part, which we call archipelagos, and then run OLAP workloads on the data parallel part, which is the data parallel archipelago. And essentially what's the interesting thing here is that as the workload comes along, you assign the right tasks to the right side, but then you have a loose job to core assignment so that you can borrow a task parallel processor onto the data parallel side if you need to do that. So just to let you in on a few of the challenges, this architecture immediately changes the situation because it raises three questions. First of all, data placement. How are you going to place data in memory? Raw, column, hybrid, PAX. It looks like the PAX deal is the best because OLTP and OLAP both agree with it somehow, but there's more research to be done there. More importantly, however, how do we make up for the lack of cache coherence? OLAP workloads are read-only in nature, so this means they don't really need to ensure coherence inside them. But OLTP workloads running with attached parallel processors need synchronization and at multiple levels for coordinating transactions. With concurrent control protocols, they have threads with latches, and then they need memory access with atomics. So the second question is, can we design an OLTP runtime that can scale well without cache coherence? And while thinking of that question, thinking of OLAP that doesn't modify data, we actually see that still there's a snapshot of the data that needs to be fresh, that needs to be seen by both sides. And there, I can think of Hyper's implementation, which forks snapshots over. So this is actually a very elegant solution to ensuring coherence at the hardware level and can be used. However, the CUDA runtime has still several issues, several limitations that don't really allow us to take advantage of this kind of technique. So we have to resort to lightweight shadowing snapshot techniques. Last but not least, there's other accelerators out there. These are implementations of some of the systems that use them. FPGAs are gaining a lot of space. They lose a bit still in programmability from the GPU side, but at the same time, they can access data just as well as CPUs in memory. So this is what's coming next. And the next 700 transactional engines, essentially, they have to take advantage of the generalization of specialized hardware, but at the same time, embrace the specialized nature that comes in from general purpose hardware. So there's a lot of great research to be done there. However, in the future, there doesn't seem to be a database transactional engine inside that can work on all processors across the board. So there will not be, again, a performant but single general purpose database OLTP engine. Instead, OLTP engines will be designed and implemented with certain hardware capabilities in mind, which will be very specific to one or more of today's trends. And there will be the component of hardware software co-designed will be more apparent than ever. Thank you.
Thank you, Anastasia. We have time for questions.
Thanks for a wonderful talk. One of the things that worries me a bit about this vision of these highly hardware-specific engines that you're talking about is the people cost of managing them. I mean, I'm just trying to think of some poor DBA who's trying to they've learned one and suddenly there's a new hardware trend and they have to learn how to cope with something that's designed internally very differently and has very different tuning knobs. Isn't there perhaps some way to find at least a better set of tuning APIs, if you will, or some abstractions to help the people actually understand how to use these things? I'm not talking about programmability for the OLTP engine writer. I'm talking about the DBA or equivalent who's got to look after all of this stuff.
So thank you. I still see two parts, though, in the question. One of them is programmability, and the other one, who's going to do it. Okay, so the first one with programmability, I would still resort back to what's happening today. I mean, you have programmability that's getting better and better in all of the components that you need to use. So you have to bite the bullet and use them. Most education programs that I'm aware of have had a CUDA course since many, many years ago, and it's a great idea if they don't to start having it. But now also for FPGAs, I think they should also go back into our education system. So it's not, I'm not talking about an option here. I don't see it as an option. I see it as a necessity. This is not a fiction, this picture. So, and here you have tons of different processors, and if you're not using them, you're just not using them, right? So somebody else will, and they will get a better system out of it. Then about who's going to do it and the different set of capabilities or aptitudes that are needed to actually do this. Well, we are the community that fuels data scientists who are a fusion between statisticians and DBAs. I think that's a much more scary combination that we have achieved to make the best, the most sought after job in the world today. I think we can definitely do it. It's just a matter of correct education to produce the right people who are going to be able to feel the system enough so that they can understand its collaboration with the machine at the right level. The important thing is to draw the line correctly at the right level. We've been drawing the line too low where we specialize. We still do specialize, but it's at a very, very low level in the vertical abstraction hierarchy of the system. We have to raise the line a bit. And I think HTAP is a beautiful application that's complex and sophisticated enough to push us to the right direction.
I have a question here. So very nice talk, thank you.
Thank you.
In your example of the two transactions that are almost sharing the same code and they share the cache as well, do you expect that the cache will detect this commonality at runtime, or this is done at compilation time? That's
So,
the T1 and T2 example.
It's at runtime. It's actually done. We have a paper, ISCA, about that, or micro, yeah. So it's at runtime. So basically, you don't really detect the commonality. You keep some sample of what's happening. It's a very low overhead thing because it's done in the hardware. You keep the sample of what transactions exist in what first level instruction caches. And when a transaction fills its own cache that it's running and starts taking the misses that we classify as capacity, because they wouldn't have been taken if the cache were bigger, right? Then this is a signal to the transaction to look for another home so that it can leave that cache nicely populated for the next one in the group that needs that code.
Okay, thank you.
Still related to that two transactions problem, I wonder for the two transactions, you show a nice diagonal arrangement to accelerate the process. I wonder if there are three transactions, how do you want to arrange it, or how do you expect to arrange it?
You're talking still about Slick and Addict?
Yes.
Yeah, if there are three transactions. So if you have more transactions than just two, you can take them as they go along, as they come along. You assign them to the first core that has a good sample of instructions that they need to use. And another interesting twist we've made to this algorithm is to actually group them already into groups of similar transactions that they are about to execute the same code and schedule them in such a way so that they can take advantage better of the cache locality. The important thing here is that the transactions go after the cache locality, so we don't have to move instructions up and down the memory hierarchy at all.
Donald Kosman from Microsoft.
Nice to meet
Hi.
you.
Yeah. Okay, so it seems that you've been mostly concerned with single machine, what happens within a machine. Of course, we're more interested in at scale, and we see that a lot of the energy and inefficiencies go because we have some machines that are very utilized, but others not, and that we need to design to smear around the whole workload across machines. And my question is whether this kind of has a higher priority and would lead to totally different designs, that you need to kind of decouple your storage architecture and in very different ways that might be at odds with the techniques that you described.
So I've been mostly preoccupied with what happens in the same machine. mostly because what happens is so much that I haven't had time to get out and look at the next machine and how they communicate. With in-memory work that is with which we do these days for OLTP, it actually makes sense to work in the same machine to see how the one machine is utilized and see how we can do it, make it better. And I think I made a pretty convincing case about what is good. Now, you're right in the sense that when you need to transfer stuff across different machines, and especially when you need to transfer data, and especially when you have to exploit different configuration, the problem amplifies itself. You add a new dimension to the problem that needs to be researched. The answer is yes. I didn't talk about it today.
Sang-Hyun Cho, Samsung's memory business. I understand that you want to integrate a large amount of DRAM, and you want to also reduce the power consumed by the humongous DRAM system. And this is a very complex engineering problem for us. And if this engineering problem, you have to trade off certain things to get some other benefits, right? So if you want to get power benefits, what do you want to trade off if I say bandwidth from DRAM, latency from DRAM, or the contiguity in the physical address space?
What was the last one?
The continuity in the physical address space.
Continuity in the physical address space, then bandwidth, then latency.
Thank you.
Okay, let's thank our speaker. Thank you, Anastasia. Our next speaker is Professor Andy Pavlo from Carnegie Mellon University. So Andy is actually at the beginning of his professor's career. It seems only yesterday that he was, on the same stage taking his ACM SIGMOD Jim Gray Best Dissertation Award at SIGMOD 2014 in the area that was all about scalable transaction processing in these new large-scale main memory database systems. So we are very excited today to have Andy back here telling us about some of the exciting work that has been going on in this area since then. Welcome, Andy.
Thank you. All right, so good. So this morning, I'm going to talk about an issue that's sort of been in the back of my mind for some time now. And this is overwhelming realization that nobody really cares about the research we're doing in concurrency control. And with a few exceptions, obviously, but what I mean by this is that we in the SIGMOD community, and by extension the BODB community, are publishing papers on concurrency control that has little to no impact on real-world systems and real-world applications. So I feel like we've just been sort of polishing the ball for the last couple of years, and I want to talk a little bit about what we can do to break out of this. But actually, before I get into this topic, I want to say that this is a big deal for me to come and speak in front of everyone here, in front of this whole general SIGMOD audience. And the SIGMOD chairs are actually worried about giving someone who is junior faculty without tenure a speaking slot because they were worried I was going to come up here and just pitch nothing but my research, and it would not be interesting at all. And try to help my tenure case. So they required me to agree that this talk has to be professional and that I have to limit myself to only 3 plugs during the entire talk. So plug would be like a pitch for my own paper. And so they asked me to put a little bell up that'll ring every single time I do a plug. And this is how they're going to keep track. And they said if I go over 3, they're going to pull me off stage and embarrass me. So with that in mind, those are the rules. Let's get started. So concurrency control is obviously an old topic in the world of databases. In the early days in the 1970s, concurrency control was used for helping the database mask the slowness of reading and writing data from disk. And so for this talk, we're only going to focus on single node databases, but a lot of the same concepts still apply in the distributed systems. So there was some great pioneering work done by Jim Gray and the System R team at IBM, and they showed how you can implement these things inside of a real system. And then the great Phil Bernstein came along a few years later in the late 1970s, early 1980s, and provided us with a more formal framework for how we can reason about the correctness of these concurrency control protocols. And he essentially showed that there's basically 2 categories. There's the pessimistic ones and then the optimistic ones. So with in-memory concurrency control, we have to actually rethink about how we want to design these protocols in our systems, because now we can assume, the database system can assume that all the data you're going to access is in memory. So how you would do certain things in a disk-oriented system where you'd have to account for stalls are no longer an issue in in-memory databases. So there was some early work done in this area in the 1980s, especially at the University of Wisconsin. And we saw some of the first commercial in-memory databases come along that supported concurrency control and transactions in the 1990s. Some of them actually still are available today. You can still get Oracle ×10 and Altabase. But for most of them, as far as I know, they've been sort of relegated into this maintenance mode because through acquisitions. Like AT&T had Dolly and DataBlitz, and there was SolidDB, and that was acquired by IBM, and then they divested that a few years later. It wasn't really into the late 2000s, early 2010s, that we saw this renewed interest in in-memory concurrency control and in-memory databases. And this is because the hardware actually finally caught up, where it's now possible to store all but the largest databases entirely in main memory. We also saw this advent of multi-core CPUs, where we now needed to account for multiple transactions running at the same time with different cores, rather than worrying about multiple transactions sort of interleaving their operations when installed to go to disk. So I'm highlighting here what I think are the three most important concurrency control protocols and systems of this era, and I've categorized them loosely into whether they are partitioned or non-partitioned schemes. So the first system that sort of came around in 2007 is the HSTOR system that I helped build when I was in graduate school. And this system basically identified that the cost of accessing a tuple in main memory is the same as cost of acquiring a lock for that tuple. So the system is better off just ignoring the locks and only accessing the data. So they had this single partitioned, single-threaded execution model where you split the database into partitions and have single threads execute those partitions without any concurrency at all. So then you don't have to set any low-level locks and latches. And you're essentially running the transactions at bare metal speed. So this works really well if your database can be partitioned cleanly, such that most transactions only have to access a single partition. But not all applications can be split up like that. So the other category of protocols are ones where it assumes that the database isn't partitioned at all, and you have a single global database. And so the Microsoft Hackathon project was sort of one of the first ones that have come along and showed how you can build a high-performance OLTP concurrency control scheme for an in-memory database that isn't partitioned. And Microsoft had to do this because they couldn't take the HSTOR model, because that means that some applications from the customers would get great performance, but some of them actually would do worse. And you wouldn't be able to find out until you actually bought the product, so that would be a tough thing for them to sell. So the main point about the Hackathon project is they showed how you can set the locks and latches directly inside the tuple headers themselves in memory, and then you don't have to have a separate lock table as you would in a disk-oriented system. A few years later, the Silo system came out, and this system was a variant of using optimistic concurrency control, and they showed how you can reduce the amount of communication between CPU sockets while you execute transactions, and that's how you get great scalability and great performance, as Natasha showed in her earlier slide. Most of the papers that come out on concurrency control in the last couple of years have been mostly based on Silo. Everyone seems to be tweaking Silo and trying to make it run faster. So the main theme of this talk, though, is that although we did this great work a couple years ago, this has not really, the additional work we do beyond this has not really had a big impact in industry and in real-world systems. And I will say the feedback that I continually get from people running real databases is that all this great concurrency control research we're doing at SIGMOD and VLDB is great for classic OLTP applications, for finances, for banking, and things like that, where you really need high-performance transactions running major changes. But for a lot of other applications, this work is completely not relevant to them at all. And as new applications and new fields emerge, people aren't interested at all in what we're actually doing. And so in many cases, we're writing papers, we read them, but then nobody else actually builds upon them. As a quick aside, I will say that there's another topic to discuss where it's not clear people even want to use transactions at all, let alone the ones we're providing them. So Peter Bayless has done a great work that showed that real-world applications don't even use transactions at all. And the ones that actually do use them don't even use them correctly. And we've done a similar study in the CMDBAC corpus, which is a project we developed at CMU, which is a plug. And we've shown that the popular web frameworks that everyone's using to build their applications, like Django, Ruby on Rails, and Node.js, none of these applications are using transactions at all either. So there's another topic we should discuss about whether people actually even know how to use transactions. And I'll say that if you're interested in this topic, you should go see Peter's talk today at 10 a.m. right after this session. So now I'll say I'm not a co-author on this work. I just think it's really good. So this is not a plug because it's not my work, but I'll say it's a half plug, right? Okay, so what's the feedback that I get from people that say our concurrential research is not useful and doesn't matter? Well, they say there's two assumptions that we're making that are not realistic. So the first assumption is that we assume that all transactions will execute as stored procedures. So that means that instead of running with a conversational API like JDBC or ODBC, where you have the application server initiate a transaction, send a SQL request, get back a response, do some more processing, and so forth. Instead, we assume that the program logic for those transactions are embedded inside the database server itself, and now the application only makes like an RPC request or invocation to the database server to invoke that transaction, and then it gets back the final result of that procedure. The second assumption is that we assume often in our research that all transactions execute with the serializable isolation level. So now when we teach in the undergraduate database course, we teach the virtues and the benefits of serializable isolation. We say this is the gold standard of what you want to achieve in your database system because it allows the application developers to not worry about at all the correctness of their programs or whether their transactions are going to read inconsistent or dirty data. But in reality, people say that most applications don't actually need serial isolation or don't care. I lost. Okay, that's awesome. Okay, great. So the feedback I keep getting is that these two assumptions are not as prevalent as we think they are. So to understand this disconnect better about what we think about in our research versus what happens in reality, we actually performed two studies this last semester where we want to examine what goes on in concurrential research and what goes on in real systems. So the first study we did was my students and I examined all of the proceedings of SIGMOD and VLDB from the last 5 years, and we looked for papers that were dealing with transaction processing or concurrency control. So this is not all papers are proposing a new concurrency control model, but rather are they proposing some kind of method or an algorithm or system architecture that had something to do with transaction processing. And in total, out of the 1,800 papers we found, about 95 of them were dealing with concurrency control or transaction processing. So of those 95 papers, we found that 73% of them are running transactions using stored procedures. This is not saying it's the primary API, how you invoke transactions, but this is sort of one of the main assumptions that they're making. We next found 57% of them assume transactions run in the serializable isolation level. So again, this is a bit more nuanced because sometimes in the papers they run at different isolation levels, sometimes they do experiments showing different things. But for this, we assumed that, is the paper showing that they want to run transactions in a serializable isolation level, and we couldn't determine whether the protocol required them to run a serializable isolation level. We just looked for this assumption. So now putting these two things together, we found in total about 50% of all the papers that we looked at are making both of these assumptions, that they assume transactions are going to run as stored procedures, and we assume they're going to run with the serializable isolation. So now, given this, we next need to go and understand what actually happens in the real world. So although we are building a new database system at CMU, we're not a business, we don't have customers, so we can't ask them directly, how are you using things? So we instead decided to commission a survey of database administrators to ask them how applications actually use their databases. So for this, I had to go get IRB approval from the university because we are doing, asking questions to live human subjects, and I had to go through training to make sure I was doing the right things and going through the right protocols when we talk to the DBAs. And I'm happy to say I'm actually now certified at the university to do experiments of both database administrators and prisoners. So we chose to do database administrators first. So for this, we asked them a bunch of general questions. We had over about 70 responses from different DBAs. And the results I'm showing here are only correspond to the DBAs that work on databases that are doing transaction processing. So that means that if they were running a data warehouse that wasn't doing transactions, we sort of were excluding them from these results here. So of the 50 DBA responses we have, they managed about 79 different database installations. And I'm showing the top 5 database systems that were in our responses, and they are basically what you would expect to see, right? The top 3 database vendors and the 2 major open source systems. And then we had a smattering of about 9 other different database vendors that they were using. And I'm happy to say also too, we had somebody down in Tennessee actually respond to us that was managing an IMS database that wasn't the US government and wasn't a major bank. So we were pretty excited to talk to him. So I would say that I wanted to be able to share the results and publish everything for you guys during this talk and make it available online. We still have to go through the IRB protocol to anonymize everything. So the goal is hopefully this summer, we can either put out a blog article or a tech report and share all our results with everyone here. But for now, I'm just going to show sort of a rough overview of what's relevant to our discussion for this talk today. So the first question we asked them is, what percentage of the transactions in the applications that are running on their database systems, what percentage of them are run as stored procedures? And so what we found is that a large majority of them are not using stored procedures at all. Over 50% of them are either not running any stored procedures or running less than 10%. So, and this obviously contradicts what we saw in the survey of the academic papers. So one thing I would say is the trend we expected to see, which we see here, is that as you increase the percentage of stored procedures, the number of databases that are being run like that go down. But what's surprising is the spike at the top level, 76 to 100%, where we see actually an increase of database systems. For this one, we don't have a good answer yet why this occurs. I mean, one installation was VoltDB, which always runs everything as stored procedures. But we haven't gone back to the DBAs and talked to them a little bit more to see out what's going on here. But we guess because they're sort of, they're guesstimating how many transactions are running stored procedures, this might be why they're selecting this higher number here. So we've done some basic analysis about looking for correlations between the other questions we asked about their applications and databases with this question here. And what we find is that there's no notable trend in things like the age of the application's code base or the application field they were actually running in. So we expected to see that older applications would actually be using more stored procedures, and we don't see this as the case at all. The only thing that actually is correlated is that what database systems they're actually using. So we found that without really being surprising, that people that are running MySQL don't really run with a lot of stored procedures. But most of the 100% ones are either Oracle or Postgres. And then SQL Server and DB2 are sort of scattered in between. So that's the only really strong correlation that we found at this point for these results. So now the next question we asked them is, what percentage of the transactions execute at different isolation levels? And for this, we asked them to loosely categorize this in terms of no transactions, few, most, or all. And so for this, the results are that most of the transactions are running under read committed isolation. And this is not surprising because this is the default isolation level for a lot of different databases, right? For MySQL, for Postgres, for Oracle, for SQL Server. By default, you get read committed. What's also interesting to point too is that at no case is anybody saying that all the transactions running in their database system are running at serializable isolation. Right? So this contradicts that assumption we saw in the academic papers. And so for this, the only correlation that I found so far is that the application age is the only thing that actually determines what isolation level you run at. We'd actually find that the older the application is, like 10 years or more, you're more likely to run at read uncommitted, and actually more likely to run at serializable. But again, in terms of different database vendors, our systems, our application fields, it's sort of all over. The finance guys seem to run at serializable and read uncommitted, right? And not a lot in between, which is pretty interesting. All right, so we actually also, ask DBAs whether we can go back and ask them additional questions about their responses. And so we did do that and asked them, why did they make this, why are transactions running at, the isolation level that they selected, or why they're running with or without stored procedures. And the feedback that in general that we got in the case of stored procedures is that most DBAs don't want to use them because of sort of obvious software engineering challenges. Right? They're difficult to write because you're writing them in sort of a language different than the application server. They're difficult to test. They're difficult to debug. And a lot of DBAs also said to us that they did not want to allow their application developers to push new stored procedures to the database system all the time. Right? If you have an agile software development environment, you're updating your application maybe every 2 weeks, every month, and that means new stored procedures every single time there's an update. And DBAs didn't want to take those changes all the time without vetting the actual code first, because they wanted to make sure that they had a stable environment that provided stable performance. So these are sort of obvious. We sort of knew this ahead of time with stored procedures. In terms of why they don't run with serializable isolation level, I will say that there was no sort of common thread or theme in all the responses. It was sort of all over the map. But the only two major things I can point out that sort of seem to occur the most often is that DBAs had no idea why they weren't running with serializable isolation. They just said that this is the way it's always been done. And I suspect that they just ran the transactions under the default isolation level from their system. Results seem to be okay, and they just let it go. The other response we also got to was that it was not worth the overhead or time or effort to actually go tune the database system to actually make serializable isolation run faster. The DBAs are super busy. There's all these other maintenance tasks they have to deal with, and it didn't feel like it was worth it to go make serialized isolation work faster. They just ran it at a lower isolation level, and that was good enough for them. All right, so what's the impact of this? So I would say that I don't think it's necessary for us to assume anymore in our concurrency control research that transactions are always going to execute with stored procedures and are always going to need serializable isolation. And the reason is why you don't want to do this is because it actually changes the bottleneck that you end up optimizing in your system. And so you end up optimizing things that aren't as important as you actually thought they were. So now I know some of you are sitting here thinking, well, hold up, Andy. I've read actually some of your papers. And aren't you being basically hypocritical here? Because aren't you assuming, aren't your other papers assuming that you make these same assumptions? And I will say, yes, I totally admit that I'm guilty of this. I'm probably the worst offender of this. If you go back to the list of papers where they were running both with stored procedures and serializable isolation, 11 of these are mine, where I'm either a co-author or the main author on. So I'm totally guilty of this, right? Now, some of you also may be thinking, well, isn't this all bullshit because didn't you get hired at Carnegie Mellon because of your concurrency control research? And to that, I would say, no, I was actually not hired because of this. The reason I was hired is because I lied to them at the university, and I actually told them I was Greek. So if you don't know this, Natasha used to be at CMU. And when she was there in the 2000s, 4 out of the 4 database professors at the University of Pittsburgh and Carnegie Mellon were all Greek, right? So when I interviewed there, I just assumed that they want a Greek person. So I just told them I made a fake Greek name, and I told them I was Natasha's long-lost cousin, and they bought it, and that's how I got hired. Right, so it's not because I assumed stored procedures and serializability, right? But this is actually causing a problem, and I'll bring that up at the end. Okay, so where do we go from here? So I would say that in the next 5 to 10 years, I think that we don't need to polish the ball anymore. We don't need to try to tweak Silo to make it run just a little bit faster. There are other interesting problems, there are other interesting challenges that we should be looking at in our research. And so I want to propose 3 items I think that are relevant, and I'll talk a little bit about what is involved in each of them. So the first thing I'll say is that whenever we do papers on concurrency control, it's not enough just to look at the protocol, right? We need to look at how transaction processing affects the entire architecture of the system. So by the protocol, I mean whether you're using two-phase locking, whether you're using optimistic concurrency control, right? I mean there's other things going on in the system that are impacted by transactions. And a great motivation of this is a blog article from Uber from last year where they talk about how they went from Postgres to MySQL. the full story about Uber is that they went from MySQL to Postgres back to MySQL, but they don't, for our purposes here, that doesn't matter. And in this article, they talk about how the reason why they switch from Postgres to MySQL is the way that Postgres manages secondary indexes and how it's affected by the transactions that they run in their workload. And so I would say that when we do a paper on concurrency control protocols, we need to look at the other facets of the system. So secondary indexes is one thing. If you're doing multi-version concurrency control, you should look at the version storage and the ordering of versions in memory. And then you also need to look at how you actually do garbage collection for these older versions, right? Because these impact the performance by a lot. So to give you a quick example of how this works, this is a paper we published in VLDB this year, which is a plug, and where we implemented a bunch of different configurations of MVCC from a lot of the major database systems, and we ran them all inside of our Peloton, which is the new database system we're building at CMU. And so if you look at the far end of the graph, when you're at the maximum concurrency on this box at 40 threads, you see that there's actually a pretty wide difference between the different configurations, right? So that I'm saying Oracle, MySQL, and all these other systems. I'm not actually running the real systems. I'm just running their configurations inside of our own system. And so in this case here, for this particular workload, at the top, you see Oracle, MySQL, and the NeoDB configurations are performing the best, but you see Postgres is actually performing the worst. But all four of these systems all use multi-versioning with two-phase locking. So they're running the same concurrency control protocol. It's the other things I mentioned in the other slide, the version storage, the garbage collection, the secondary indexes, that matter more for how these systems perform when running transaction workloads. So I would say it's important for us to consider the entire system when we do concurrency control research. The next thing I think is important is that we need to make sure we look at and examine the communication overhead from the application server to the database system. Again, if you're assuming everything is stored procedures, you don't have multiple round trips between the application code and the database server. But now, if you don't have stored procedures, now this actually becomes the bottleneck, right? It's the JDBC, the ODBC protocol going back and forth. So one of the things that we found in our survey is that most of the applications are running in the same data center as the database machine. So that means we don't see a lot of them running in different geographical regions. There's not a lot of them also running on either the same box or the same rack. So that means that this is sort of the scope of the problem we need to consider. So I think there's a lot of interesting research to be done on how to optimize these client-server protocols using kernel bypass methods, like RDMA or Intel's DPDK toolkit. And I think there's also some work to be done in using artificial intelligence and machine learning where we can do aggressive prefetching for transactions that have very common patterns and start pushing some of the results to the client side as soon as possible when we see the first query. So we don't have to wait for the multiple round trips. And then the last one is that is actually an older problem. And that is we really don't understand how applications are affected by running at lower isolation levels. So I mentioned Peter Bayless's work that he's published in SIGMOD this year. Alan Fettke has looked at this problem a few years ago as well. And there's that great, of course, critique of the isolation level papers from the 1990s where they talk about these things. But we really, up until this day, we really don't have a full understanding about what's going on with these applications and how they're affected by isolation levels that aren't serializable. And so I think this will be a combination of both theoretical research, systems research, and possibly even field studies where we go and look to see, well, how dirty does the data actually get? Maybe it doesn't matter at all. Maybe recommitted is good enough. Or are people spending a ton of time cleaning their data over and over again because of these problems? So I think a really interesting challenge we should finally solve after all these years is really understanding what these isolation levels means in the real world, in real world applications. So to finish up, I still think it's a really interesting time to do concurrency control research in databases, but I think it's important that we work on the right problems. And one of the ways that we can make sure that we're guided in the right direction is that if we work on actually real systems that are actually being used in the wild. And traditionally this has always been a problem because the major systems have always been closed source and proprietary. But I think there's a lot of interesting systems that have come out in the last 5 or 10 years, both in the US and abroad, that are open source. So you actually can make an impact by trying to figure out what's going on in these systems and make them work more better and correctly. Another side comment I'll say too is that I think that we need, as a community, a better way of collecting information about applications. So I should have showed my example of my survey here, but that's sort of an ad hoc thing we did as a one-time for this keynote. But I think it'd be nice to be able to understand what do actually real transactions actually look like, and have this sort of be something that everyone can look at and model in their experiments, rather than just running TPCC or TPCE. So I would say that this actually has to come from an academic institution, because the commercial guys can't do this because they have to be protective of their customer data. Right? The only people that actually probably know what real world applications look like are the cloud service providers, because they know what every query is, but they can't share that with us. So I think we need to think about a way to be able to leverage the fact that in open source systems, maybe we can collect some of this data. And as a quick final point, I'll also say that I didn't talk about these papers here, but there was actually great work that had a lot of impact done by Michael Cahill and Alan Fettke on serializable snapshot isolation. And of course, Dana Body's deterministic currency control, which I think are actually really interesting protocols that have actually found themselves be implemented in real world systems. So in case of Cahill's work, SSI was actually implemented in Postgres a few years ago. And then for Dana Body, his work was actually implemented in a database startup called FaunaDB. And they're actually running with they're leveraging the work he did with Calvin in their startup, which I think is pretty exciting. All right, so with that, I'm happy to finish, and I'll be happy to answer any questions that you have. Mohan's right here. He's ready.
Thank you, Andy. You basically reiterated at least one of the major points I made in the original Aries paper, which was it's important to consider concurrency, recovery, and storage management together in order to come up with very good algorithms and so on. So the original idea of doing layering and all that doesn't cut it for that reason.
Was that a question, or is this...
No, okay. I was just saying you are basically reiterating stuff that I had mentioned quite a while ago, and people haven't been paying attention to that aspect of the Aries paper is my point.
Yes. First of all, the Aries paper is 70 pages long. You say a lot there.
This is at the very beginning, and this is a major point of the paper.
I'll put your picture on the slide next time, all right?
Hello. So really nice talk.
Where are you? Sorry, I can't see you.
Here. Hi.
Okay, stand up. Yeah.
Yeah. So so I have discovered over the course of my career that people are very lazy. So if you give them a default of read committed, they'll use read committed.
Yes.
If we had high performance serializable transactions and that were the default, they would use that. Now, so that's point one. Sorry, this will be a question eventually. So the other thing, second observation is I've worked on, since I live in New York City, I have worked a lot for finance companies where you'd think that they would care about these things. And they say, oh, there are errors in the database anyway, which I found really peculiar, because why have a database if you're not going to care about the quality? But then once they were convinced that really they could find big problems with read committed, they were willing to be convinced and did try to have serializability when they could. So I guess my question is, you're saying we should look at the practice and conform to it in our research. I say we should make serializability, as all your papers have done, make serializability fast, make that the default, make it easy to debug the stored procedures, and help them do the right thing. Could you agree or disagree?
So is your question, do I agree with you?
Yes. Yeah, do you agree? See, because you're really advocating, look, abandon all this stuff and just do what people are doing and do it better for them. And I'm saying no, we should make it easier for them to get high performance as well as correctness.
So, I mean, there is a, yes. So I would say that I feel that there's two sorts of ways to think about this. There's one is there software available that people to use? And certainly I think in the NoSQL case, we missed the boat on this because, there was no open source distributed transactional database, right? People are coming along with Cassandra and all these other things that didn't do transactions because that was the only sort of thing available. And the new SQL systems, more recently, this has changed. So, yeah, so yes, I suppose you could say, yes, if we just made it better and available, people will use it. But I would say the history shows that's not the case, right? And we don't have a good understanding yet also whether recommitted actually matters or whether is actually good enough, right? These DBAs are not, you know, these are not sort of small startups. These are, you know, big banks and big companies that have a lot of money. If they really cared about correctness, they would have run in serializable, right? But they don't. So we need to understand why.
Sorry, just one little small follow-up. So this was consulting for big New York banks, right?
Sure.
International banks. The DBAs are not thinking like the people who are on the bottom line. They're just thinking, let me get through the day.
Yeah.
So they're doing read committed because that was the default and because it made things a little bit faster.
Sure.
But when you actually showed them that there were errors, you know, they said, oh, please don't tell anybody because then I'll get in trouble. Really, this is how it works on Wall Street. So they said, please don't tell anybody. If we made it faster and that were the default, then good things would happen.
So I would say I'm not, right, I'm not saying that we should throw away serializable, right? I'm saying we should understand the different options a bit better. I would certainly say, though, stored procedures that's going to be a hard hurdle to overcome, and we need to make sure that that all the research we're doing works well with, you know, the conversational APIs, because that one is definitely most common, right? Switching isolation levels, if we made it faster, they just go flip a switch in the database system, and then they get, you know, go up to serializable. Switching to stored procedures is a major overhaul of their application code and is a major rewrite that most organizations are not probably willing to pay the penalty for.
So do you have a sense of how far are we in terms of bridging the gap of performance using serializable isolation, and how many of those use cases did change from serializable to a lower isolation level because there was no performance?
So your question is, how far away are we in sort of modern concurrency control for in-memory databases from having serializable be almost the same performance as recommitted? That's a good question. I would say that I don't have results to show here, but in some preliminary studies that we've done, the whole sort of networking stack, the front end of the database system, is actually the major bottleneck that we need to fix. So I would say there's some engineering things, but I think there's some more sophisticated things we need to do to sort of to cut that down. So I have a good sense of, like, if you get rid of stored procedures entirely, how fast you can actually go. And I would say Hackathon, you know, supports serializable. I don't know what percentage of their customers actually run that, though.
We have a question all the way from the back.
Yes.
Hey, Andy, good talk.
Yes.
I like Dennis's comment. I hope you asked the DBAs how much shame they felt with lower than serializability. But my question for you is, I only saw 2.5 plugs.
Oh.
You said 3. What happened?
Oh, yes. Sorry. I completely forgot. Thank you. Yes. So yeah, I still have MAGA. I still have a half plug. Okay. This is my student Joy Ruraj. I think he's the one in the glasses. I get confused with my students. So CMU found out that I'm not Greek. It was a really easy test. They put baklava in front of me, and I didn't know what it was, and they were like, all right, he's not Greek. So this is my student Joy. He's actually better than I am. And the problem is, because I'm not Greek, they actually want to get rid of me now, and they want to hire him. So I need to get rid of him. I need someone to hire him so they don't replace me with him. So that's my final plug. Okay, so he'll be on the academic job market. What's that? That was not a planted question, Mohandy. I don't know what you're talking about. Oh, Phil has a real question. Yes.
So I got the feeling that a lot of the DBAs you were surveying were from large companies, big users of database systems. But most of the new applications I hear about are in areas like IoT, games, multiplayer games, large-scale telemetry apps, social networking apps. A lot of those apps do a lot of their application programming either in JavaScript on the client or in large mid-tier applications that scale out to a large number of servers. I wondered whether you did any surveying to get a feeling for what those folks are doing with their databases, or are they just all doing record-at-a-time key value store operations?
So I don't have a breakdown to show you of the different application fields. I say there are some people into these newer fields, IoT and game companies. And your question is, what do their transactions look like? Yeah, so we did ask them to specify whether their transactional workload was read heavy, was it write heavy, or was sort of balanced. And I would say that the transactions that are just ingesting data, those are very simple, and then they do analytics on them. So in those cases, running a read commit is probably good enough because they're just inserting things.
Right, so maybe these are the sorts of applications we ought to be looking at to,
correct, yeah. So
to optimize, and they're very different because they're running with cloud storage typically, so there's a long latency to get to storage. They're highly distributed, so they're running two-phase commit across a large number of servers, et cetera. So it leads to a very different workload profile.
Right, so yeah, I mean, Phil has done awesome work on doing transactions in Orleans, his actor database. Yeah, so I'm not discounting that. I'm just saying we were sort of looking at sort of, classic OLTP, those kind of workloads. So I absolutely agree with you.
All right, let's thank our speaker. All right, thank you to our great speakers this morning. So without any delay, we are going to transition directly into the lightning talks. So what I'm going to do is I'm going to ask everyone who is presenting a paper this morning